All right, so I have a quiz open. This is the last quiz you guys took. And just want to show you one thing. Oh yeah, you did fine. So this thing popped up, right? Did it pop up for you?
Yes. Yeah. I was using a different browser and I didn't have cookies enabled, so it just didn't show.
If you click question help, you can view the instructor tip there. So if it's a show work problem, I've tried to put instructor tips in, and if you're using Chrome, it should work. So try to use Chrome when you take these quizzes. So this instructor tip says you may use a calculator for assistance. So if it says that, what does that mean? You can do all the row reduction in the calculator. Okay? Not very many of you did that. You did that to check, but you turned in the work. You turned in all this handwritten row by row operations, which is fine. I'm okay with that. I'm just saying, unless it says you have to show the row by row operations, you don't have to. You can use the calculator to do the row reduction. I want you to do that, okay? Because this question is asking something different. You know, if I want to test you on row reduction, I'm going to say, show me all the row reductions and show me all the steps. But if I'm not testing you on that, I'm testing you on something else, and I want you to use the calculator to make your life easier. I want to know if you understand the other stuff, okay? So this one said you could use a calculator. I mean, it told you you could, but to show, how do you show your work if you're using a calculator? You show the beginning matrix, show the reduced matrix, and then whatever else you have to do to answer the question, okay? So make sure that if you do use a calculator, then make sure that you show the starting matrix, the ending matrix, and then whatever else you have to do to answer the question. Some problems you can't row reduce in the calculator if there's a variable in there. The TI-84 or 83 won't work. But if I want you to explicitly show all the steps, step by step, it'll say that. It'll say show all your row reduction steps, okay? Like it did in the last quiz, right? The last quiz it said that, right? Let's look at the last quiz. The first quiz, I guess. On this quiz, do all row reductions by hand without a calculator, okay? So that's like explicitly telling you to show all the steps for all the row reduction steps, okay? And you'll get one like that on the test. I mean, you're going to have to show on the test at least one problem where you have to row reduce everything by hand. And if it doesn't say this, but it has an H in there, that's what you're going to have to do anyway. It has H and K in there. So just know how to do it. But if I'm testing on something else, then you don't have to. It'll say you can use a calculator. Everybody okay with that? Any questions? I sent everybody an email. I extended 1.5, 1.7, and the quiz, the third quiz, by 1 day. Okay. So I hope that helps. So last time we started talking about transformations, and in particular matrix transformations. So we have this transformation T. It takes R2 vectors and turns them into R3 vectors. And when you plug in an R2 vector, you're plugging in the two components. And then out, you get three components, and the three components are calculated by doing these operations to those two components. So the first component is the difference of the two components of the vector you're plugging in. This one is 3 times the first vector, the first component, and this is -1 times the first component plus 2 times the second component. So you can define this transformation by matrix multiplication. So you can turn this into a matrix multiplication problem, and this would be the matrix that you would use. Now look at the matrix and look at this definition and tell me how to do it, how to write the matrix. Yeah, these columns represent the coefficients of x1 and x2. That's it. And it's a 3 by 2 matrix, right? That means whatever we multiply by has to be what size? 2 by 1, those are R2 vectors, right? If it's a 2 by 1 vector. And what vector is going to come out after you multiply? 3 by 1, so that's an R3 vector. Right. So it says check to make sure these are the same by multiplying this matrix times x1 and x2. So let's try it. So my new vector will be 3 by 1. I'm going to use the dot product method instead of the vector weight linear combination method. So this first component will be the first row dot product with this vector. So 1 times x1 plus negative 1 times x2, that's x1 minus x2. Okay. The second component will be the second row dot product with the vector 3x1, 0x2, that's just 3x1. And then the third component will be the third row of the matrix times the vector, dot product with the vector, negative 1 x1 plus 2x2. Is that the same? This is just another way to write this. This is an ordered triple. Right? We're writing our vectors like this most of the time in this vertical way. This is a horizontal way to write it. In trig class, you made these sharp brackets, and in physics, you might write them that way, or engineering, I don't know. But they all mean the same thing. Okay. Okay. So what are the domain and the codomain of T? The domain is all the vectors that you can plug in to the transformation. It's like what can you plug into the function and get an output? So the domain is all R2 vectors, right? You can multiply this matrix times any 2 by 1 vector. So the domain is R2, any R2 vector. Any vector that has 2 components, that's what R2 means. And then the codomain is what type of vectors come out after you multiply the matrix times the vector. They're 3 by 1 vectors. So any vector that has 3 components is called an R3 vector. So it's all R3. Well, the codomain is R3. The range may not be all of R3, but the codomain is. Are you okay with that? The codomain is just the type of vectors that you output after you do the transformation.
Why is that R3 then?
Because when we multiply, we get a 3-component vector. Right? So we plug in a 2-component vector we get out a 3-component vector. So we plug in an R2 vector, we get out an R3 vector. You can plug in any R2 vector, you can multiply the matrix. What you get are R3 vectors, that's the codomain. The range would be the actual vectors that come out. You may not be able to get all R3 vectors from this transformation. In fact, you can't, because these don't span R3, right? These don't span R3, so they span a plane, so the range will be a plane in R3. But the codomain is not that. The codomain is just what type of vectors, what space are you going to be in when you output. You're going to be in R3. What actually gets outputted is the range. Okay? Domain is everything you can plug in. And here I can plug in anything. The domain is what type of things come out. What are the outputs? What do they look like? What space will you be in when you output? And the range is the actual set of the outputs. Okay. This is the picture. Domain R2, range is R3. I mean, codomain is R3. These are the type of things that come out. But the range is just a plane in this case that's in R3. Okay. So given u is the vector -1, 5, find t of u, the image of u under the transformation t. Now you can go through this thing and find it. Okay? But that's not the purpose of this section. We want to just multiply by the matrix, right? Just multiply by this matrix, it's going to give you what you want. So we're going to multiply by our matrix A. So T of U is the same as multiplying that matrix times U, because it's a matrix transformation. So I got to remember what that was. 1, 3, -1. 1, 0, -1, 0, 2. Is that correct? So we're just going to multiply the matrix to find T of U. And T of U has another name. It's called the image of U. It's called the image. You know, U lives in R2 space, and the transformation T sends it to R3. So it's like you're saying you're projecting an image into another space. So we're calling the image the transformation of U under T. Okay. All right. So we're going to get, again, a 3-by-1 vector. I'm going to use the dot product method for multiplication. But you know that you can just multiply the first column by -1, the second column by 5, and add those together. That'll work. Okay? But I think it's quicker to dot product. So I'm going to take the first row dot product with this column. So -1, -5, add them together, -6. -3 and 0. This is +1 plus 10, 11. So that vector, it's an R3 vector, and it's called the image of U, and U is that R2 vector. It's just an R2 vector. Yeah, it's just a vector with 2 components. But we turned it into a vector with 3 components. Okay. So D says determine if this R3 vector is in the range of T. So the range is the set of all vectors that you actually get outputted from this transformation. And we want to know, is this one of those? So that means let's call this B. We'll call this vector B. Is B in the range? So we need to know if this equation has a solution, right? If we multiply A times a vector X and get B, right, then B is in the range. So we need to solve this equation for X. We need to find X. Actually, all we need to do is show that the system is consistent, right? So I've made a matrix system. I just need to show that there's a solution. And then, we might, it's okay to find the solution. That's fine. So what I'm going to do is augment A with B. So, is that correct? My memory good? I'm going to augment with this vector. And remember, I'm looking for these two, x1 and x2, right? That's X, my solution X. If I can find that vector, then that means it is in the range. So I'm just going to use the calculator. This one doesn't look too bad to row reduce, but let's just do this anyway. It's 3 by 3.
It's nice to be able to check my work with the calculator.
Yes. It's also nice to check the calculator with your work. Because I messed up, didn't I? What you get out of the calculator is not the gospel, right? You could have entered something in wrong. The calculator has to do algorithms to approximate. It does the best it can, but it's limited to its memory. It's limited number of decimal places. You are not limited because your brain can fathom infinity, maybe. You don't have to store a bunch of data to do some math, right? You can just say this is square root of 2. You don't need to write out all the decimals of 2 and store it somewhere, which you could not, because it goes on forever, right? You could not store all the decimals of square root of 2, but you can just write square root of 2. Right? So, other calculators can. This one cannot. This one can't do that. So, you could run into situations where, the calculator might even not be able to do the calculation you want. It might run out of memory and actually error. You may get it locked in a program. It won't stop trying to calculate something because you give it something too bad. If you put a matrix in and raise it to the 200th power, it might just not do it. Okay, so so you can do things calculator can't, and the calculator only does what you tell it to do, right? So if you tell it to do the wrong thing, then it's going to be wrong. But it is nice. Instead of talking, I should have just row reduced by hand. I've wasted all this time. Got on my soapbox. All right, so we get this. What does that tell us? No solution because it's a system that stops here that's augmented here, right? Some of you are getting confused about where to draw this line, or if you're supposed to or not. Okay, so this is a system. I augmented here. That means no solution. So the answer is no. It's not possible to multiply A times a vector and get that vector, that -3, 0, 5. So that one is an R3 vector that's not in the range. It's not in that plane. So this is no. So that's B is not the range of T. It's not one of those output vectors that you get. Everybody okay with that? Okay, E says find an X, and X is in bold, so that means it's a vector, in R2, whose image under T is given by this vector. So how do I do that? Yes, we're going to do exactly the same thing we did on the previous problem. It's exactly the same question. It's just asked a different way. We're going to do the exact same work, but the goal here is to find the X. It's not just to show that there's a solution. Does that make sense? But we're going to do the exact same thing. That's what I was talking about earlier. We're going to be very picky about what you say in your answers. Okay? Because if this one had a solution and you just wrote X equals blank, that's not really answering the question. You're supposed to say, is it in the range? Yes, it is. Okay? And this is the justification for it. Okay, so we're going to do the same thing. We're going to augment this vector and row reduce, and we're going to actually find the solution if one exists. So I'm going to use the same A. I'm just going to change the last column here. Should be 8, 15, -11. Okay. I get this. So 1, 0, 0, 0, 1, 0, 5, -3, 0. So we have to write X. So yeah, first, how big is X? Yeah, it's R2, right? Some of you get in this mindset that that's always the solution. That's not right. Okay, you're looking at the rows. X1 is 5, X2 is 3. This doesn't help you one bit. Okay. So, and it tells you it's an R2, right? So you just have to be careful when you look at these that you're using the right size vector for your solution. So this has 2 columns, so there's only 2 variables in that matrix. So there's only 2 in the solution, right? So this is 5, -3, and it's an R2 vector. So that's the X in R2 that when you multiply by A it sends that vector to R3, and that image is 8, 15, negative 11. And if you want to check your answer, you multiply A times 5, negative 3, and you should get this 8, 15, negative 11. That's what should happen. If you want to check your answer, you're going to take matrix A, multiply it by 5, negative 3, and you'll get 8, 15, negative 11. AX equals B, right? This is the image. This is the image. Okay. This is the vector in the range, the domain, sorry. This is the vector in the domain that you're sending to the range. You don't have to know this. This is also called the pre-image. We just kind of get dumb when we start naming things. Okay. We need a name to say we're projecting this image, so we call that the pre-image. But it's just a vector in the domain. It sends it to a vector in the range. That range is part of the codomain. Okay. Is X unique? Yes. Because we got one solution. We didn't get infinitely many, right? So there's only one of these that works. It's only one vector in that domain that will map to that vector that's the image. Okay, there's only one.
Factor out and it had a inconsistent variable in the bottom row, say it equal something, would it be not in the range?
Yeah, the X would not exist. Right? You could not find there's no X that works. Yeah. And that would mean that this image is not an image. It's not in the range. If you had no solution, if this was no solution, then right, no solution. If there's infinitely many, that's okay. You just got infinitely many vectors pointing to one image. That can happen. Yeah. Any questions? So, we're getting to the point where you have to be real careful about the terms and the definitions of what things mean, okay? We're not doing anything different, right? Then we started, the very first day, we started row reducing. And we're going to keep doing that. We're just going to keep doing that all semester, okay? It's just going to call it different things. We're going to use it to do different things. We're going to make up words and we're going to do different things, okay? It's close. Yeah, but we're gonna do other things. We are gonna do other things, but we're always gonna row reduce. Like we're gonna keep row reducing all semester. Okay, we'll keep row reducing. We'll keep multiplying by matrices. It'll just be what question's being asked and what am I supposed to do to answer it. That's what's gonna be hard. Okay.
More the operation idea behind it.
Yes. The operation's not going to be difficult. If you got a calculator, we're not going to give you these 20 by 20 matrices to do, okay? So we're not giving you heavy calculations. It's going to be, the hardest calculations that you do, you've already done. It's that row reduction by hand, okay? It's the hardest thing you're going to do calculation-wise. Now, conceptual things, we're going to keep getting more difficult, okay?
While we're kind of talking about the meta of this class, is there any other branch of mathematics that deals with graphical representations of things above the third dimension?
No. This doesn't do that either.
Well, it touches it.
We can't graphically represent above the third dimension.
You could have an X forward, I guess.
Yeah. You know, if you keep going, okay, you will have classes where you will you'll have 4 variables in your function, you know, you might have two inputs and two outputs, like an R2 vector to an R2 vector, okay? That gives you a four-dimensional graph when that happens. So you can't graph from one to the other like you can if it's just X and Y. You can graph on a two-dimensional plane, right? So what you can do is graph the domain and graph the range and see how the domain changes when it goes to the range. You know, what is happening to the range when you plug in the domain. And you can look at those two, or you can look at three-dimensional domains and three-dimensional ranges and see what is going on, but you can't graph the in-between like you can in 2 and 3 dimensions. So if you have 2 variables, 3 variables, you can graph it. You can graph what's going on. You can graph the relationship. But if it's more than that, you can't. You can graph what happens before and after if they're in 2 or 3 dimensions, but you can't graph the in-between. You can't graph the relationship between the two. But you can still describe it with math. Okay? You can still describe it with these transformations and functions and whatever. You just can't graph them. Now, there will be graphical, quote-unquote, representations of problems that are multidimensional, that are higher dimensional, but they're just diagrams. And you can take those diagrams and make matrices out of them. Yep. Yep. So when they used to do college football rankings with computers, there's a famous matrix called the Colley matrix that was used to rank teams when they used to do the BCS, right? So that was a matrix that had every team had a row and a column. So it was 120 by 120 matrix that was computing all their strength of schedule. You know, how well they did in their games, how well they did against other teams, and it was an iterative process where it was, you know, it changed until, you know, there was a program that would change the matrix until it settled out, and it would get a ranking for each team. So that's something you couldn't graph, but you could draw a diagram. You could have this huge sheet of paper and draw all the teams and draw lines. This team beat that team, and that team beat this team, and what was the score? You know, you can do it that way. You could draw a diagram with all that on it. Yeah, it would. But you could draw it, but that wouldn't be a graph of that relationship between, you know, it's a different thing. Okay. You guys are throwing me off track here. Define the transformation T as T of X, where T of X is equal to a matrix A times X, so it's a matrix transformation, and here's the matrix A. And we want to know what's the domain and codomain of T.
So is the domain R2?
Let's see. What size is A? 2 by 3. So what size does the X have to be? Has to be 3 by 1. So the domain is R3. It depends on the matrix A what size they are. So the number of columns of A is the size of the domain. It's how big the vectors are in the domain. And what is the codomain? So if the vector X is 3 by 1, and those have to be the same, right? This is the output, 2 by 1. So that means the codomain is R2. The codomain will be R2 vectors. So we're given U, and we're asked to find T of U, the image of U under the transformation. That means what? That's what I'm talking about, right? We're either going to augment row reduce, or we're going to multiply by the matrix. So you need to know what we're doing. You know, T of U is A times U, right? That's the definition that we, and it's also an R3 vector, and we just said that's the domain. So we give you these clues, but we don't come out and say, hey, multiply this. Okay? That would be nice if we did, right? But we're not. We're saying, find the image. The image is always the output. The image is the output. So find the image. So this is going to be A times U. So A, let me write down A. And we're going to multiply that by U. I mean, if you were to do the wrong thing, if these dimensions aren't the same, then you'll be able to tell right away that it's not going to work. You can't augment these, right? Because they're the wrong size, right? They're the wrong size. So, we have to multiply them. And if you were supposed to augment and you need to multiply, you would, or you tried to multiply, it might not match up. But if it's the same, if the codomain and the domain are the same, you won't be able to tell that right away. Okay, so I'm going to get a 2x1 vector, right? I'm going to dot product each row of A with that vector U, and that'll give me the components of the new vector, the image. So first row, dot product with this column. 5 plus 6, 11, plus 7, 18. You check it, I might make a mistake. Now the second row, 15 minus 3, that's 12, minus 7, 5, 18, 5. So that one is in the range, right? That's the image of U. So we took an R3 vector, we turned it into an R2 vector. Okay? This is in R2. This is the answer. Just this, right? Just that's the answer. You don't have to write in R2, but I'm just telling you it is.
That's the image.
That's the image of U. So what we're saying is if we plug in U into this transformation, we get this vector out. We call that the image.
5, 3, 1 is X. Right?
Yeah,
Okay, X.
that's U. That's U, yeah, right here. We're plugging in that. Yes?
So how do we know what's going to happen? We just did get multiplied up.
The dimensions wouldn't match, right? Because this is 2 by 3 and this is 3 by 1. We know we can do it because those are the same. But if those were not the same, then it wouldn't work. You wouldn't be able to do it. Okay. C says, find an X in R3 whose image under T is 7, negative 14. So what are we going to do? This one we're going to augment and row reduce, yes. So augment and row reduce. We're looking for the X. And they're giving us the image. They're giving us the output. We got to find the input. So we're going to augment and solve. And I forgot what my matrix is. Thank you. I forgot. Negative 7, 7. We're going to augment. Right?
Can I stop and ask a question?
Yeah. Sure.
In the homework, 1-4, question 6, answer, I think, is right. It was asking what is the X that makes a certain matrix equal the output or the augmented part of it. You know what I'm saying? Make those. What X do you need to multiply the matrix by to get this certain output or whatever? I just instead of figuring out like using the dot multiplication thing or the dot product, I wrote things thinking that I was supposed to do that, and I accidentally come up with the two top numbers because the bottom row is zeros, but the top two is 5 and 1 on the end on the augmented part. That was also the X. Is that like that? I mean, you see what I'm saying? Like when you
My guess is that you're misremembering what the question's asking.
find out.
Yeah, you need to look at the question, find out exactly what it's asking, and then you may have done the right thing and not realized that you were doing the right thing. So you need to read the question and make sure that it's, exactly the right. Do you know exactly which question it was?
Yeah.
Which one is it? Number 6 on which homework?
I'll look at it.
Let's look at it now. Which homework?
I think it's
1.4, number 6. Yeah. Let U be this vector. A is a matrix. Is U in the plane in R3 spanned by the columns of A? That's the same question that we're asking in this section. Right?
Yeah, but it also it's asking what the vector is.
Right.
Multiplied by. That's
Yeah.
what I'm talking about.
Okay.
Put those augmented matrix there.
This is the output. It's asking, is this in the output? The output, if we're spanning these, we're multiplying by x1 and x2 and creating all linear combinations of those two vectors, right? And that creates a plane in R3. And we're asking, is this in that plane? It's the same thing as asking, is this the definition of the matrix transformation? Is this an image? Is this an image? And if it is, find the vector that you multiply by this matrix to get that image.
So when I put those together,
You augmented those and row reduced and found the x.
the bottom row was zeros, and the augmented parts of the third column was 5, 1, and 0. 5 and 1 was
Yes. Yes. You did the right thing.
That's basically any x equals u.
Yes. Yes. That's exactly right. Again, we're going to keep doing the same things over and over. Call them different things. This question is the same question that was on that homework problem in 1.4, but we're in 1.8. Okay? Find an x in R3 whose image is this, right?
I just kind of struggle how to see that when you row reduce that out, why does that come up with the vector that you're looking for?
So if you multiply A times a vector x, you get another vector, right? This is an R3 vector, and this has to be R2 because of what the matrix looks like, right? So we're given this one because it's telling us the image is 7, negative 14. We're replacing A times X with this notation that we're doing a matrix transformation. We're treating it like a function instead of a system or instead of a just matrix multiplication. We're saying it's like a function. You're plugging in a vector, you're outputting a vector, right? So they gave us this one, and we have to find that one. So we're solving this system, right? We're solving this system for X. And X is an R3 vector. Well, we have 3 variables right here that make up our solution, okay? We're trying to find that X1, X2, and X3. And if you were to multiply A times X without the dot product rule, if we didn't do the dot product thing, we would multiply the first column of A by X1, the second column of A by X2, the third column of A by X3, and add them together. And we need to find the right X1, X2, and X3 that will give us 7 and negative 14. Right? So yeah, it's the same thing. Yes. No. The fact that you realize that is perfect and was good for the whole class. Right? It is the same thing. You're doing the same work. You're answering a different question. Okay? But it's an equivalent thing that you're doing. You know, you're solving for x in a system ax equals b, which is what we've been doing all semester. You know, but we're going to think of it in different ways. How is it going to help us do different things? Okay? And that's what these questions are about, is to see if you understand. We're not trying to make you row reduce 100 million times, even though that's what you're doing. You know, we're asking, do you understand these concepts that we're trying to teach you? So what size is this? 2 by 4. All right, so what we get. So we get a free variable, right? Did you know we were going to get one before? Yeah, we talked about that last time, right? If you have more columns than rows, then you're going to get a free variable. Right? So we get a free variable. So we're going to solve for x1, x2, and x3. We don't have to do, we don't have to do parametric vector form. We'll just see what do we have to do. So x1 is negative x3 minus 3. X2 is 4x3 plus 5. And x3 is anything that we want it to be. The question is, find an x. Right? Yeah, let's plug in 0. We just need one thing that works. We need one vector that's going to work. Infinitely many will work. And we've written out how to find those. But that's not the question. The question is just says find one of them. You know, find an x. So let's plug in 0 for x3. Let's see if I can do it here. And I'll write this in a vector. I'm squeezing it in, yeah. So 0 for x3. 0 here, that'll give us 5 and negative 3. So there's a vector that'll work. If we multiply the matrix times that vector, we'll get 7, negative 14. And if we plug in 1 for x3, we'll get a different vector. That vector will work too. Okay. You've got R3 space going into a plane. Okay. So I think it makes sense that you'll have infinitely many vectors pointing to one vector. Okay. I mean, that's got to happen. Okay. So is the x you found in part C unique? No. Determine if this vector is in the range of t. What we're going to do here? Augment and row reduce. saying this is in the range is the same thing as saying this is an image of some vector. Okay? So 1, 3, 2, -1, -7, 7. We're going to augment with 9, 8. Before I row reduce, before anybody does it, are we going to get a solution? We have to, right? So this left side is going to row reduce the same way every time. The right vector will change because we're plugging in a different vector on the right. But all this stuff will stay the same. And what does this tell you? The first two vectors are linearly independent, right? Because if we just put those in a matrix and threw everything else out, the first two vectors will row reduce to this 1, 0, 0, 1, so they are linearly independent. So if I have two, if I have two linearly independent R2 vectors, what's the span of those two vectors? R2, right? If I span those two vectors, I get every vector in R2. I don't actually need the third vector, right? The third vector's in there, that's okay. The third vector getting thrown in there means you get infinitely many possible solutions. If you just had the first two, it would just be one, be a one-to-one thing. But what that means is it doesn't matter what R2 vector I plug in, it doesn't matter what R2 vector I pick, I'm always going to be able to find a solution, an X in the domain, because just these two, if I just find, I can find a linear combination of those two to get any R2 vectors because they span R2, right? They span the whole thing.
So if you had that third vector, you no longer do that.
No, I get infinitely many instead of just one-to-one. I just add more possibilities. Well, there are three vectors, right? So I get because I broaden the space that I'm using, I get more possibilities. If it was just R2 to R2, then I would just get one solution. Adding the third variable is what I was trying to say. The third column of that matrix, right? Okay, now I'm going to row reduce. I didn't change my matrix. Yeah, sorry. What am I doing? I got to preaching too bad. That's right. Don't trust the calculator all the time. Always check your matrix when you plug stuff in. Okay, I'm going to see if I can get fractions. Yep. It row reduced the same way on the left, right? It's out. It always does that. And then I get this on the right side. So the question is determine if it's in the range. So is it?
Yeah.
Yeah. So we don't have to actually solve it. We can just say 9, 8 is in the range. Yes. Because that system has a solution. I can find an X I can multiply A and get 9, 8.
Also because there's two positions, the one in each row.
Yeah. As long as you get a solution, then it's in the range. You can find. Yeah. Yeah. Now, I knew that. I didn't know if y'all knew that. Okay, so we went ahead and did it, just to show it, and I explained that it doesn't matter what R2 vector you pick, it's always going to be the range of this T, okay, of this transformation. Yeah, because you can multiply by 0 and get 0, right? Yeah. So I mean, it's called trivial for a reason. Okay, very, very important topic. Linear transformations. So we just had, we talked about transformations. They're like functions, but with vectors. We have matrix transformation, so we took a transformation, turned it into matrix multiplication. And now we have what's called a linear transformation. One of the most important properties in math is to have linearity. It has nothing to do with a straight line, okay? Has a little bit to do with it, but not much. So a transformation is linear if it satisfies two properties. So the first property is that if you take the transformation of a sum of two vectors, you get the sum of the transformations of those two vectors separately. So it's like a distribution property, but it's not really distribution. We're not multiplying. Okay, we're not multiplying T unless it's a matrix. So if it's the transformation of a sum, you can split it and do them separately and then add them together. So you would say the transformation of a sum of two vectors is the sum of the transformations of those two vectors. And then secondly, if you have a constant multiple of a vector, when you take the transformation of it, it's the same as taking the transformation of the vector and then multiplying by the scalar. So you can pull that scalar out. You can factor the scalar out. And you can combine this into one statement. You could say it's linear if the transformation of C1u plus C2v is C1 t of u plus C2 t of v, right? You just do both of them at the same time. So that's kind of an equivalent way to say linearity. Okay. So it's a linear transformation if you can do this. This is the first scalar. This is the second scalar. I had to pick two scalars. I didn't use C twice because they can be different C's. They can be different scalars. Or you can call this A and this is B, this A and that B. These are vectors, and the others are scalars, right? Do you know anything else that has this property? What else does? Integrals, right. When you take an integral of a sum, you can just do the sum of each individual term, right? And if you have constants in there, you can factor them out of the integral, right? What about derivatives? You can do derivatives the same way, right? Unfortunately, in this class, we won't get to this, but you can think of functions as vectors. And you can talk about functions as being linearly independent. And, linear combinations of functions. And can you span functions? You will have solution spaces. And, you will get to that a little bit in differential equations. Okay? Because you'll have differential equations that have infinitely many solutions. And it turns out, you can create those by spanning functions. Right? So when I took linear algebra, we talked about this, but it's not in our course. So I'm sorry. Maybe I can change that for the next group. I don't think the other teachers will let me. Okay, note that if t is linear, then t of 0 is still 0. So the 0 vector always maps to the 0 vector. So let's say let t be a transformation that takes R2 vectors and maps them to R2 vectors. Let it be a linear transformation that sends vector u to 9, 5, the vector u 9, 5 into vector -1, 2, and maps v equals -1, 4 into 3, 8. Use the properties of linear transformation to calculate t of 4u, t of -2v, and the sum of those, t of 4u minus 2v. Okay, so let's start with 4u. Well, that's the same as 4 t of u. Right? I don't know what t is, but I know it's linear. It's a linear transformation. That means I can factor the constant out. And I know what t of u is because it tells me that that's -1, 2. Right? If I plug u into the transformation, it outputs -1, 2. So I get -4, 8. Oops. B is t of -2v. So that's -2 times t of v. I don't know what t is, but I know what t of v is. What's t of v? 3, 8. So that is -6 and -16. And then the last one says do both, 4u minus 2v. Now you can actually calculate that and then do the transformation, but we don't know what the transformation is. So we don't know the definition. We can't do that. So we have to use the fact that it's linear, right? We're going to split it up. We're going to factor out the constants. And I know what 4 t of u is. That's -4, 8. And I know what -2 t of v is. That's -6, -16. So I can just add those together. Oops. Okay. So -2 t of v is that. So the negative, like this is the same as plus -2 times, right? So that's the plus sign there. The negative's already in the vector. So this is -10, -8.
Why did we use those two vectors for u and v? Why didn't we use the u equals 9, 5? Why did we use this?
Okay, that's u. But we don't know the definition of t. So we can't actually do the operation onto u because we don't know, it doesn't tell us what t is. The only thing it tells us is that it's linear. It's a linear transformation, so it has those properties. And we know these two mappings, that's it. So we know that this is t of u, this guy, because it says it sends this vector into that one. Okay? And it sends v into 3, 8. So this is t of v. So it's already, the operation of t has already happened to these two vectors. That's why we can't just take this part and just find out what that is and plug it into t, because we don't know what t is. Okay. It's forcing us to use the property of linearity. Okay. Are we good? Okay. So we want to know if these are linear. These two, we have two transformations. Let's see, there might be another one. No, just these two. We want to determine if they are linear, if they have those two properties. So we have to check those two properties. Okay. So the first property would be t of u plus v, right? We need to show that that's the same as t of u plus t of v. And we have the definition here. So let's define u and v this way. Let's say, you know, they have three components, right? So they have to be R3 vectors. So u is, we'll say it's u1, u2, u3. Does that make sense? Plus v1, v2, v3. So that's the same as this. This is how you add vectors, right? Whoops. That's a u right there. So I added the two vectors up. And what we get out is an R2 vector. So let's see what happens. You know, maybe I got room over there. I don't think I do. I'll keep it over here. Okay. So the first component is x1 minus x2. So this is my x1, and this is my x2. Everybody agree? So this is x1, x2, x3 of my new vector that I'm plugging in. So this is x1 minus x2. That's a 1, sorry. Let me fix that. Say it again, I'm sorry. That's the first component of my new vector. This part right here. Yeah. And here's my vector I'm plugging in. So I've got to take x1 and subtract x2. So I'm plugging in a sum of two vectors. And I've got to show that it's going to be the same as taking the transformation of each one. Okay. So I have two generic vectors, x1 or u and v, and I put their components in, and I added them up, but this is one vector that I'm plugging in. Okay. When you add those two vectors, it becomes one. I'm plugging in that one vector. The first component when I apply the transformation is x1 minus x2. So that's what I wrote down. Okay. Now what's the other thing? The second component? 5x3. So this is 5 times u3 plus 5 times T3. Okay? So you tell me if I'm wrong. This is the same as this. Is that the same? Is it?
No, it's B. It's union.
So I put these 3 in one vector, and I put the other 3 in another vector. We've done that before, right? And if you add those together, we get the same thing, right? Just rearrange. So you just rearrange the terms. So what is this guy right here? What is that? What is it? This is the transformation when you plug in U. Am I right? Yeah, this thing right here is T of U, right? And this whole thing is T of V. So that means this is T of U plus T of V, and that means it's the first property is satisfied. We just did a proof. That's how you do a proof. You pick generalized vectors, show that the property works. You've proven it works for any vector U and V that's three dimensions big. Okay. So what do we have to do for the second part? I have to erase. I'm out of room here. I'm erasing too fast. So for the second part, I'm going to, this is for the second condition. It's about scalar multiplication. I want to pick a C times, let's say, vector U. You could use X. It doesn't matter. I use U and V just to have different ones, okay, for the U plus V. So C times U, that's going to be this vector, right? We have to plug in a three-dimensional vector, an R3 vector. And I'm multiplying it by a scalar C. So I'll multiply each component by that C. The transformation says to subtract the first two components, multiply the last component by 5, and that makes up your two components of your new vector. I'm just really erasing fast here. Come on, baby. There we go. Sometimes you have to talk to it. Okay, I got 1 minute. So this is right, which is the same as this. Do you agree with that? So that's C times the transformation of U. That satisfies the second condition. So this is linear. Okay. I'm not going to do the second one. I'm out of time anyway. Yeah, just a minute. This one's not linear. So can anybody tell me why?
It has no exponent.
No. It's just this 3, the constant 3. So what happens if you add two vectors where 3 is the second component? Well, let me see here.
Parallel line.
So if you do TU plus TV, right? You're going to get a 6 right here, not a 3. Right? Oh, the examples are switched. Okay. Well, sorry. So you try it out and see. It won't work because of that. Okay. Okay, I'm done. Sorry to keep you late. Yes.